Hey, we're back again for the last of the revision topics. Hope you have had some time to look over the previous ones. Some hard ideas there. Might need some help with the teacher. This little revision topic here on equations and formulae should be a bit easier. It's basically covered in year 10 pretty well. So here we are, equations and formulae. That's the Latin for formula. And sometimes we anglicise that to formulas, so that's okay too. What are they? Well, equations, I think we've seen a few equations in junior algebra. Here's a linear equation, 3x plus 2 equals 0. We could subtract 2 from both sides and then divide by 3 and get a solution to that equation. We could plot that on a number line. Couldn't we? Neg 1, this would be neg 2/3 in here. We could plot that solution. So equations do have solutions or roots. Sometimes we call them solutions or roots of an equation. What's another one? What about a quadratic equation? X squared plus 5x plus 6 equals 0. Might have done this in year 10. This is where we can use our factorisation skills, like this, just checking the expansion there that it is correct, and then by the null factor law, either x plus 3 equals 2 or x plus 3 equals 0. Hang on, by the null factor law, we'll just get rid of this here. Okay, by the null factor law, one of the factors must be 0 or null, because two things times can only give 0 if one of them is in fact 0. So we've got this solution or this solution by the null factor law. Nothing to do with rugby. Small joke, NFL. Anyway, not to worry. Let's move on. So we have done a bit of work with equations. There are also things called an identity, something that's always true no matter what the value the variable takes. So we'll see those a bit later on with some other functions we'll be doing. Here are some here where if you have x plus y squared, all squared, take 2xy, it always comes to this, no matter what values of x and y you put into that expression. Okay, so what about a formula? Well, here's some down here, the area of a circle. Now that involves a constant pi and the parameter r. A parameter is really some property of the system. We let r stand for the parameter which is the radius of the circle. So to get the area of a circle, we multiply r, or the square of r, by pi. So there are many others here. A distance between 2 points on the Cartesian coordinate system, volume of a sphere, do you remember that one? So formulae will enable us to work out a value of a particular property of the system, and given other values, other parameters, given those values of those parameters, we can calculate that. So we have several different variations here, all evolving around an equal sign, I guess. Equations have equal signs in them. You're equating two things. Formulae have equations in them because you're saying what something is equal to, so that you can calculate it. So let's go down now and have a look at this. Something that we often want to do is to rearrange a formula. Rearrange a formula to make a new subject of the formula. Make a new subject. So here in the first one, let's say we really want to solve for b. As it is at the moment, a squared plus b squared equals c squared. The subject of the formula is c squared. So if we can isolate b by itself now. So here we could say, well, b squared, we remove that a squared, b squared will be c squared take a squared. So I've isolated on b on a side by itself, and then to get b back from b squared, we'll take the square root. But don't forget, there is a positive and negative square root here. And we're solving an equation that looks like this. X squared equals 4. There are two solutions, positive or negative 2. Because 2 squared is 4 and neg 2 squared is also 4. So don't forget, there are two roots to an equation like this. The principal root, which is a positive, and the other one. Now, if b was a length in our problem, we did this before, if b was a length, you use the principal root, the positive root only, because a length in a diagram can only have a positive value. Right, let's look at this last one here. T is 2 pi square root of L over G. I'd like to set this out over here and just talk about a little bit of basic algebra here. So here L over G. One way that is quite convenient to solve equations is to rearrange equations, whichever way you want to put it, is to list what's been done to the variable which you want to make the new subject. There's L. What's been done to it? It's been divided by G, and then we've taken the square root of it, and then we've times it by 2 pi. And we got the answer T. Now, let's work backwards here to solve an equation algebraically. We usually unpack those steps. So let's reverse this one first of all. Let's divide by 2 pi. So T over 2 pi would equal the square root of L over G. And then reverse this one. Let's remove that square root here. Let's square both sides. Okay, squaring both sides would bring us back to L over G. Squaring a square root sign removes it. Opposite operation, inverse operation. The first step was to divide by G. Let's now times both sides by G and reverse that. So we've got G T squared on 4 pi squared equals L. Problem solved. So if we wanted to actually write this equation with L as the subject, that's how we would do it. Do you recognise that formula? Have you done some physics? This formula is formula for the period of a simple pendulum. So somebody who might want to make a pendulum of with a different period of oscillation might want to use this formula, because it's set up to tell you the length of the pendulum for a particular period. All right, let's keep going down now and see what they've got for us down here. Now, we can graph equations and graph the solution on a number line. Let's take this one here. X squared equals 2x plus 8. This equation comes to be neg 2x take 8 equals 0, doesn't it? Moving all terms across the left hand side. And now we can use our factorisation skills to solve that. And the result must be a negative 2, so let's make the biggest factor negative so it wins. Neg 4 and plus 2 in here. So that means x take 4 by the null factor law must be 0, or x plus 2 is 0. So x is 4, or x is neg 2. And we can plot those solutions. That's our solution set to that equation. We can draw a graph there of our solution set. And here, just watching this, we're doing the IB now, so they like this notation. The solution set is x as a member of the set neg 2, 4, with our set bracket around it. This set bracket, okay, we'll just come over here a little bit. The set bracket, which encloses the values that we have in our set. Okay, so what about the solution set of a two-variable equation, that's something like y equals x squared. So, for example, if you took y equals x squared, this is the graph of y equals x squared, and here there will be two values that fall, or a point will have two values, an x value and a y value, so that the point falls on the graph of given by that equation y equals x squared. So here the equation y equals x squared describes, if you like, the pattern or the rule which the points must obey to lie on that shape, must obey to form that shape. So you can't just put any x and y together and produce that shape. It says if x is -2, y must be -2 squared, or 4. If x is √2, y must be the square of √2, or 2. If x is -4/5, y must be the square of that, which is 16/25, a positive 16/25. Okay, so they are, if you like, the solution set of the equation y equals x squared. Or you could say that is a formula describing the rule, or giving the rule which points must obey to form that particular shape. So many ways of talking about these things. Okay, well, let's have a look now at some equations of lines. And I hope these are friendly to you, because this is really year 9 and 10 work now. And a linear equation, I don't know, you probably have been given things like y equals mx plus c, or y equals ax plus b, things like that, and sometimes we write it in what's called the general form, that form there, and we have various properties of those lines. And so let's have a look over here. The slope or gradient of a line is the vertical change over the horizontal change, y step over x step. Have you seen that before? So if we wanted to find the slope of this line, we could take, as I have done here, the two of the points, and I think what have they used here? One take -1/2, use these 2 points to find the y step. So the y step over the x step, so it's going to be 1 take, what is it, -1/2 over x step, 4 take 1. So that's what they're doing over here, and hopefully you have done that in year 9 and 10. So you can find the slope. So the slope in this particular case will come to 1/2, and you might rewrite the equation in a different form. Do you remember y equals mx plus c form? The slope is this number in front of x, and the c is the y-intercept. So you could actually put this 1/2 x plus, and what's the y-intercept? -1. So we'll just get plus 1/2 x plus -1, or if you like, just 1/2 x take 1. And if you were to rearrange that, the original one, sorry, x take 2, y equals 2, then what would you do? Let's say here we subtracted x from both sides, and then we could divide by -2, get -1 plus 1/2 x. So you can see it is valuable to be able to convert between forms. And the mx plus c form, this form down here, has the advantage of being able to read off the slope very easily. Anyway, we'll come back to that. Let's move on and have a look at the various equations or forms of the equation of a straight line. The general form, what we just referred to there, ax plus by plus c equals 0. And you can put every equation in that form if you want. Notice that a and b wouldn't be 0 there if you wanted an equation of the general form of a straight line. Here, the mx plus c form, remembering that m is the slope and c is the y-intercept. Point slope form, yes, quite often used, but generally we expand it and put it back into this form. So here you use a known point on the line, y1 and x1, and then create that particular form of the equation. Horizontal lines, let's just recall those. A horizontal line goes through like this. So y is always a constant. So let's say this was 3. The equation of that line would be y equals 3. Or in general, y is some constant value. What about a vertical line like this? It's not too vertical, mate. So let's say that goes through at 3 on the x-axis. This would be x is equal to 3. So x equals a constant is a special case of a line, and that's got a simpler formula. So we want to be able to do two things. We want to be able to draw the graph. Here it is here. Draw the graph if we're given an equation, and given a graph or some information, find the equations. Okay. They are suggesting here that for the first type of problem, they use the slope-intercept form. That's not a bad suggestion. For the second type of problem, the point-slope form is better. So let's have a look at doing some work with that. Okay, so here's an example. Without using a calculator, a graphics display calculator, sketch the line that is the graph of each of the following linear equations written here in general form. So this one here, what would we do? Well, you generally, we could put it in as they have done here, the slope-intercept form. I don't really think that's the easiest way of drawing that graph, because here what we could do, 5x plus 3y take 6 equals 0. A good way of doing it is to change that to that form and then talk about the y-intercept is when x is 0. So 3y would be 6, y would be 2, and the x-intercept is always when y is 0, so that means 5x would equal 6, x would be 6 over 5. I don't know whether that might be a better way of saying, well, okay, y equals 2 there, and this is 1 1/5 here. Well, it's hard to say, isn't it? If you do change it to the y equals mx plus c or slope-intercept form, you can map this neg 5, 3, go 3 in the x there, and neg 5 in the y. So that's a way of mapping a line using the slope-intercept form. The next one, y take 4 equals 0, well, you can say rearrange that y equals 4, so that's going to be this horizontal line up here. Find where y is 4 on the y-axis, and then the line always has y is 4. So it's got to be a horizontal line, and just have that equation, y equals 4. X plus 3 equals 0. X is neg 3, so go to where x is neg 3 on the x-axis, and then we have this vertical line. Alright, so you hopefully have played around with some of those before. Let's keep going now and have a look at another example. this is now finding the equation, given some information about it. Find the equation line passes through the point 331, has a slope of 12. Write in slope-intercept form. Well, the best way of doing that, I think, is, well, they have done it this way. I think probably something is preferable, is to say, well, here the slope is 12, so y equals 12x plus c, and then substitute in 331, and so 31 equals 12 by 3 plus c, or 31 equals 36 plus c, and here therefore neg 5 equals c, and therefore y equals 12x take 5. So that might be the quickest way of getting that. Overall, though, you need to be able to do a couple of different methods. Find the linear equation given that in C and F, knowing that when C is 10, then F is 50, and when C is 100, F is 212. Solve for F in terms of C. Well, what they're doing here is saying, can you get a formula instead of Y's and X's, using F's and C's. So let's have a look at the slope. The slope of the line here would be equal to, now F in terms of C, it's the F step, if you like, over the C step. So here the F step is 212, was it 212 take 50, over the C step is 100 take 10. Okay, and so we get here whatever that comes to, 212 take 50, 162, over here 90, and when you cancel that down, that actually comes to 9 over 5, I think. Is that true? Yep, so it's 9 over 5. And so you have the formula, what? F equals 9 over 5 C plus our little c down the bottom there. Let's just come down a little bit. And then if we sub in one of the points, let's sub in the point here. What have we got? 1050 might be the best. So here put 50 equals 9 over 5 times 10 plus c, which is 50 equals 18 plus c, or 32 equals c. So our final formula, this is actually a formula converting degrees Celsius to Fahrenheit, if you remember. So that's doing it another way. The way I think might be best for this one is to use the formula m equals y take y1 over x take x1. It's a slight variation of this one here. And put in the slope is 9 over 5 equals y take. So the difference between the y's here, y take, let's say 50 over x take 10, using the point 1050. And so if you do that, you get 9 over 5x take 9 over 5 times 10 equals y take 50, and so on. So not there, it shouldn't be there, this is x, but we'll go back in a minute and have a look. 9 over 5x take 18 equals y take 50, and then 9 over 5x take 18 plus 50 plus 32 equals y, and then change it back perhaps to f and c, because we have a contextual problem here with c's and f's. So you could do it that way. do it in X and Y land, and then come back to C and F if you get confused with the idea of F's and C's. So that's something we need to build up to compared to Year 10. Let's have a look now at the slope of a line and whether lines are perpendicular or parallel. If you have parallel lines, obviously you would have the same slope. So the slopes in parallel lines are identical. They are equal to each other. So they must always be that way if they're going to be parallel. So you can see here, this one has coefficient of x equal to 3 over 2, and so does this one. So every time, what does 3 over 2 mean as a slope? This is the y movement, the y step, if you like, over the x step. So if you move 2 in the x, you should move up 3 in the y. Oh yes, that checks. What about this one? Move 2 in the x from here, you move up 3 in the y. So some graphical idea or picture of what the slope or gradient means is useful. So it's worthwhile remembering that ratio. The slope is the vertical step, or the y step, divided by the x step. And generally we look at creating that by doing the x step first, as I did here. Take a point on the line, move in the x 2, and then move up in the y 3. Over here now I notice they haven't actually proven this property of perpendicular lines. Perpendicular lines have the property that the product of their slopes is neg1. As a consequence of that, one gradient or slope is minus the reciprocal of the other. So if this line has a slope of 3 over 2, the perpendicular line has a slope of neg 2/3. So that involves understanding something called rotations, which are something that is in this course later on, and not to any great extent, where you look at the relationship between lines that have been rotated through 90 degrees. At the moment, we'll leave that proof and simply go with this result of how to determine whether two lines are perpendicular. Alright, so have we got some exercises yet? Not yet. We'll go to distances and midpoints and things like that. You might know that from our introduction to modulus, meaning the actual distance from the origin on the number line, then obviously if you want the distance between 2 points and you don't care about which direction you're going in, you want the modulus or absolute value of it. So it doesn't matter which way around you take them. If you take 4, take neg 2, so what have we got here is 6, but you could go neg 2, take 4, which is actually neg 6, but you don't want a direction here, you want just a size, so you take the modulus of it. So distances between points on the number line are fairly easily calculated. Doesn't matter which way round you take them away. Neg 2 take 4 be neg 6, but you know the distance really is just the value 6. Or if you get 4 take neg 2, that will give you positive 6 directly. Now that's easy on the number line. But what if the line is angled to the two axes, is oblique line here? Then what we need to do is to use Pythagoras to find the distance. So here we want to find the lengths of these two sides, the difference between the y's. It doesn't matter which direction you take it in, we just take the size of it, and here the difference between the x's will give us that. And then we could say, well, hang on, by Pythagoras, the length of the hypotenuse, the square of the hypotenuse equals the sum of the squares of the other two sides. So it becomes x2 take x1 squared plus y2 take y1 squared. And it doesn't matter which direction you put these in. Here the Pearson's is saying you just want the length of it. It doesn't matter whether it's positive or negative, because when you're going to then here make it positive, sorry, with the modular sign you're going to make it positive. Doesn't matter whether the difference in here is positive or negative, you're going to make it a positive number, and then you're going to square it. So the distance is actually the square root of x2 take x1 squared plus y2 take y1 squared, just by Pythagoras. So hopefully you have seen that last year. So the crucial thing there is that it doesn't really matter which order in which you take away the x2s and x1s here, y2 and y1, because in the end you're going to actually square them, so it'll give a positive anyway. Alright, we'll have a look at some problems involving that in a minute. So here are a couple of formulae, the distance formula and the midpoint formula. And the midpoint formula, if you remember, is for finding the midpoint of a line joining 2 points like that, and the middle is the average of the x's. So what's the average of the two numbers? It's x1 plus x2 on 2, and it's the average of the two y's. We could actually prove this, won't do it now, but you can think of this in terms of similar triangles and actually show that for that on an oblique line, for the midpoint to be in the middle there, then it's halfway in x land, halfway along here, and halfway in y land. x1 plus x2 on 2, y1 plus y2 on 2. Okay, so let's go down and have a look at some uses of what we've been doing here now. So show that the points 1, 2, 3, 1 and 4, 8 are the vertices of a right-angled triangle. Well, if they are, then you can say, well, Pythagoras' theorem must hold. Pythagoras' theorem must hold. So what are we going to do? We're going to come down here and find the three lengths of the sides, PQ, QR and PR, and we've got to do a lot of work here with our new distance formula, remembering the distance is the square root of x2 take x1 squared plus y2 take y1 squared. And so we get those three values, and now we have to check out, is the square of one of them equal the sum of the squares of the others? And yes, we can see it. Root 5 squared is 5, root 45 squared is 45, and that comes to 50, which is the other side squared. So it satisfies Pythagoras' theorem, therefore it is a right-angled triangle, and it's always a good idea to say right-angled at, and name the point, right-angled at point P, what we've shown here. Now, therefore we've found QR is the hypotenuse, and they want us up here to find the midpoint of that. So we go to QR and we use x1 plus x2 on 2, y1 plus y2 on 2 to get the midpoint of the hypotenuse. So not too bad, this stuff. Must remember the formula for each aspect. Okay, well, let's have a look at this one. So in this one, find x, so the distance between the points 1, 2 and x, neg 10 is 13. So this is using the formula again, but there's a bit missing, so let's write down the formula. So here y2 take y1 squared. Now the distance has to be 13, so let's work out the formula. x2 take x1, x take 1. Oh, that's different. All of a sudden the unknown is under the root sign, and then we would have neg 10 y2 take y1, neg 10 take 2 all squared. So that's therefore squaring both sides. 13 squared equals x take 1 squared plus neg 12 squared, and so going all scrunched up in here now. Just working all those things out, we get a quadratic equation which is x squared take 2x take 24 equals 0. If we simplify all of that, then we can factorise. We've got x is 6 or x is -4. So let's have a look at that solution. So we've got the point here, 1, 2, and x -10. So x -10 must lie somewhere on the line x equals -10. And so there are 2 points which are 13 units away, one over here and one over here. So x is 6 or x is -4, and they both must have -10 as the y coordinate. So that's an interesting variation on the problem. There is another way of doing this here. Have you ever seen this? 13 squared is 169 equals x take 1 squared plus 144. Take 144 away, 25 equals x take 1 squared. So what's x take 1? 5, or, we put implies, or -5. Okay, do you prefer this method? Don't forget there are 2 solutions to this. You can take the positive or negative square root. So here x is 6 or x is -4. Now the advantage of this method is that it always works. If the 25 isn't a perfect square, if you can't actually factorise this in here, because it's an irrational value, then you get into trouble. But with this method, where you actually isolate the square and then take the square root, it always will give you the answer. You don't have to worry about whether it's a rational root or not. So you might keep this method in mind here as a way of solving that problem. Okay, so that's a variation where you are not given the full 2 points here to work with. You're given the length and you have to work back to find one of the points. Okay, right, we're coming to the end now, and you may or may not have seen this in year 9 and 10 work. It's called working with simultaneous equations. It's saying what we're trying to do is to solve 2 equations at the same time, simultaneously. Solve 2 equations at the same time, or together at the same time, or together. What on earth does that mean? Well, it means that you're trying to find an x and a y value that obeys more than one equation. That is, you've got 2 equations, and when you find an x or y, x and y that make one equation true, they must make the other equation true. Let's have a look at the 3 methods. First of all, the graphical method that Pearson's done here first here, because this is a good idea or gives you a good idea of what this means, solving the 2 equations together. In this section we're only going to look at straight lines or linear equations. Let's come down here. Here's the graphical method where we draw the 2 lines. Now here, this is the one that's most interesting, because if we had the equation of those 2 lines, the solution would be this point here, the point which is on both lines, which satisfies both equations. If we have the lines are the same as each other, all the points on one lie on the other, so there's infinite solutions. If we had 2 parallel lines, there is no solution, because there's no point on this one which is also on this one. They are parallel. So what we're looking at here with simultaneous linear equations is we're looking for common points on the graph. Common points on the graph. So those common points must obey the rule or the equation or the formula for both lines. Now this is good to draw a graph, but Pearson's makes an interesting point down here. You can't do it very well by hand if it doesn't come out obviously as whole numbers or something. So by hand, the graphical method is slightly inaccurate. Okay. Because you're not sure that the point is exactly at 1, 2, for example, x is 1, y is 2, your pencil could have been a bit thick, you mightn't have drawn it quite correctly. What about if the point of intersection is 5, 6, 2/3? You'd never be able to read that off from a hand-drawn graph. So you can use a GDC, graphics display calculator, to actually get that point precisely, because behind the graphics display calculator in solving for that is an algebraic approach. All right, let's have a look now at example 17. Now here, use the graphical features of a graphics display calculator to solve each pair of simultaneous equations. So what we're really saying is, well, we can solve these equations by finding, what are we saying here, points obeying both equations. Points obeying both equations. If points obey both equations, they are the points that lie on both straight lines. So we want to see where the lines intersect. So they are the points of intersection. So the solution set to a pair of simultaneous equations is the points of intersection. Well, two straight lines, of course, there's only going to be one point of intersection, if that. Now here, Pearson has suggested rewriting the equations in the slope-intercept form mx plus c. Why? Because a GDC requires this form in graph mode. Requires mx plus c in graph mode. And I refer you back to Huddy Maths Middle School wiki site there for having a look at using graph mode on the Casio 9860 Plus. And that's what I've done here. In Pearson's textbook, they've used the TI. But here we're going to look at the Casio. Here are our two equations. You must get them in that form and then enter them in graph mode on the Casio. So you go to menu graph and enter those two functions. Make sure they are highlighted there. And then if you hit draw, you will get the screen here. You might have to adjust the view window. Adjust VWin to make sure they're on the screen, which is shift F3 in here. Okay, so you might have to adjust the view window so that you get a clear point of intersection. This is the dude we want in here. What is that point? What's the x and what's the y? Because that will be the solution to both equations at the same time. Okay, so down here, what have I done? I've hit up here, shift F5 to get G-solve. So to get that G-solve, it's solving the graph, shift F5, hit the shift button F5. We come down here, and what do we want? Here it is here. If we hit F5 now, that gives us the intersection point. Just hitting F5 gives you that icon intersect, and up will come the point of intersection. There's the two graphs, two equations, and the point of intersection is x is -3, y is 4. Problem solved. So if you go back to the original equations up here, this one and this one, you'll find putting in the value x is -3 and y is 4 solves, or y is 4, not -4, makes both equations true. or satisfies both equations, so that is the solution to that pair of simultaneous equations. This point, neg 3, 4, lies on both lines graphically, and therefore obeys both equations, is the simultaneous equation solution. This is very, very, very important work, particularly useful is useful where your solution is fractional. Solution involves fractions, because basically impossible to read off a hand-drawn graph. So that's a very useful tool, the graphics display calculator there. Okay, well, let's come down here a bit. There are some algebraic methods here. The first is called the elimination method, and the idea in here is to try to combine equations, so that you get only one variable left, an x or a y left in the equation. So let's have a look at these here now, at what they've done. So 5x plus 3y equals 9. If you here multiplied that equation by 4, the original equation by 4, there we'll get this new equation. If you multiply the second equation here by 3, we get this one. What do you notice? We've made the coefficients of y equal, all but the sign. They're both 12. Now, if we add these two equations, 12y take 12y is no y, and we've got 26x equals 78. So we're adding all these pairs. 26x, no y. We've done it. Removed the y term, so we can solve for x. So it's elimination. It's a trick to remove one of the variable terms, and so x is 3. Now, if we take the x is 3 and put it back in here, either one, if we put it in either one, we'll get y is equal to 2. So the solution is 3 neg 2. So that's an interesting way of actually doing it. Let's have a look at this second one here and see what happens there. So in the second one, we're going to say to obtain coefficients for x that are equal, we multiply the first equation by 2. There we get it. And then the second equation already has x is 2. So if we now try to eliminate it by subtracting the equations, 2x take 2x would be no x. Oh, hang on, the y's go out as well. So here we have 0 equals 9, which is not possible. So there is no solution. What on earth went on? Well, they were actually parallel lines. If you rearrange them down here in y equals mx plus c form, you can see that both lines had an m, or a slope of a half. So that was why there was no solution in our elimination method. One eliminated the other. Why? Well, they are parallel lines. What do they actually look like? Let's see if we can roughly draw these now. A half x take 7 over 2 and take 5 over 2. So this is down at 7 over 2 is 3.5, so it goes through there somewhere, and 5 over 2 somewhere there, and it's got a slope of a half. So that means, we'll go this way, if we go 2 in the x, we go 1 in the y. So that's one of them, and that's the other one. They've got two different y-intercepts, neg 7 over 2 and neg 5 over 2 and neg 7 over 2, but they both have a slope of a half. M is a half. So there's no solution, and that's what our elimination method showed us there are no points common to both lines, no values of x and y that satisfy the equations simultaneously or together. Okay, well, let's go down now to the substitution method. The substitution method it involves get an expression for x or y from one equation and substitute it into that spot in the other equation and sub into the other. Can you see that both methods are doing the same thing? They're trying to end up with an equation with just one variable, either x or y. The elimination method adds or subtracts them until, adds and subtracts them to remove the common term in both. Coefficient of x's are the same, or y's. This one takes an expression for x or y from one and puts it in the other equation to remove that. Let's have a look at that in action rather than talking about it. Here, now, let's look at these two, solving these two. So let's rearrange the first one and get y equals 3x plus 9. Now, if we stick that in here instead of y, what have we got? 6x plus 2 lots of 3x plus 9, and we keep simplifying that, and we find we've got 12x equals negative 16. We have done it. We have removed the y and obtained an equation in x so we can solve for it. And then, of course, once we have the value of 1, we substitute it back into either equation. So we can substitute in here x equals, what is it, negative 4/3. We could put that in either equation and both would give you the answer 5. So the solution is negative 4/3 5. Okay, or x is negative 4/3 and y is 5. They are the x and y values that if you put in either equation will make the equation true or satisfy the equation. Let's look at the bottom one now. In this one, the book has chosen to rewrite the first equation so you get x equals 3y take 2. So rearrange it so you get an x expression from 1, and then if you put that x expression in the second equation, here it is here, 3 times y take 2, replacing the x by an expression from the other equation, you create now an equation all in y's. And here, of course, you get 0 equals 0. They've chosen another special case here. So that's always true, isn't it? 0 equals 0. So what's happening there? What it means is the two equations were exactly equivalent. Didn't matter what the x's and y's were. All points on one lie on the other one. So they're actually both of the form here, y equals 1/3 x plus 2/3. You can rearrange both of them and they are the same line. So that was a bit of a tricky do, that one. Okay, so let's move down now and have a look at the questions they've got for you here. I think there's what, 30, oh, I don't know. There are 38 questions here. Okay, so let's just leave it there for the minute, those 24. And you might like to pause the presentation shortly and have a go at these problems, rearranging of formulas and so on. But I'll just bring this down here so that you can easily find that screen again and pause the presentation so you can read those values off. All right, well, let's pause it there. You might rewind and go back to that top lot. I've got the solutions down here, so we'll do those carefully here. So there's the first 11. There's the solutions there. So when you've done those earlier ones, come back and have a look and find these solutions. Pause it there. So we want all of 11. We didn't have 11 there before. Through to 14. Got a lot of descriptions. I'd like to see you working down the page rather than across the page. So Pearson's have gone across the page to save space, but the best way is to actually work down the page. Right, so you might like to freeze it there to mark those when you've done those. So let's go now and go from this one here, 14 again perhaps, because they've got alternative solutions there, down to 16, and then 17 here. Notice the TI here, they're talking about paper 1 and paper 2, because paper 1 is a non-calculator paper, so you've got to be able to do it without a calculator. Paper 2, GDC is allowed, so you can use that to advantage there. Okay, so that's number 19 done in 2 ways. Let's go down now, and number 20, 21 there. And then let's go back 21 through there to 22, and then 23. A couple of different ways of looking at it in 23, 24 through 27. There's a fair bit of work here. And then in 28, okay, through to 31 there, 32 through, so I've done lots of work for you here. Let's have a look there. Go to 33. 35 now, and then we've got various options here. I've put in the Casio. In Pearson's they've actually used the TI, but I'm mentioning here a different mode on the Casio. The Casio has Equa mode, so I want you to have a look at that and make sure you're able to use that rather than the graph mode as well. So just check 36, 37 and 38. Okay, so we've got this, the steps there, and 37 and 38, the answers are down here, but you'd use Equa mode again, and I've got some instructions there. So come down to the end, so that's the end there. Alright, well I'll leave that with you now. You can rewind the presentation, just toggle back and get on with those questions and see what you think. Well, look, that brings us to the end of the revision topics, and I'd like to give you an introduction to the first topic in the course, or it's not going to be the first topic. We'll start actually with topic 2, I think, with functions, and there'll be a presentation coming up a bit later on for that. So I hope you will join me there as we start this new course, but good luck with the revision at the moment. Keep working hard.